essentially. So the normal system, the standard system, can be rated from 3,000 meter depth to 6,000 meter depth. It has an endurance to 30 to 60 hours. It's 6.2 meters long and weighs about 2 tons. And then we are expanding the range to smaller units with less depth rating and less endurance. And to the right-hand side, that's what I want to concentrate on a bit today, is the latest development, which is a long endurance vehicle, which can stay under the water and complete a mission, fully autonomous for 50 days. And it's larger for the reasons I'm going to explain. So what do you do with these systems? You have a number of payloads. These are sensors to collect the data, which can be a multi-beam, which I showed you before, collecting information of the seafloor, mapping the seafloor. We have a synthetic aperture sonar, which gives you very high resolution sonar imagery of the seafloor, which is used in this case for detecting wrecks. Sub-bottom profilers looking into the sub-bottom. Laser profilers, which gives you very high resolution. 3D maps of structures, like a pipeline in this case. And we have opticals, which is stills camera and movie cameras. So these are the data you can get out of it. It's very popular with the community looking for shipwrecks. So this is showing an example of shipwrecks on the seafloor with a lot of debris, which can map to very high resolution. And this is the journey of the development of this system. So the initial design for the long endurance, we set out for it to work 50 days in a depth of 6,000 meters, with a focus on from shore to shore operations. So you don't necessarily need to have a vessel to launch and recover. You can launch it from the shore and collect it at the same point or at a different point on shore. Increased focus on operational robustness and situational awareness, which is necessary if you are out fully autonomous for such a long period of time. Challenges to increase the endurance and the payload. We need to have the energy and the capacity on board. The vehicle concept calls for long missions without the support vessel, so it needs to be fully autonomous and needs to make decisions by itself, so artificial intelligence plays into it. And it's much more complex to operate and to plan missions with these systems. So the solutions we came up with, it's a free flooded architecture. So the housing is not pressurized. We have pressurized housing for the individual components inside, but not for the whole vehicle. It's powered by lithium-ion batteries, and it has multiple processors. The payload sensors, we stuck to what we know, the proven payload sensors, and we have the similar navigation architecture than the current vehicle. And we reuse existing pressure housing and have similar recovery mechanisms and the same sensor options as the previous systems. But what is different? The battery and payload capability needed to be increased. Redundancy, if any system fails, there needs to be a backup plan, and we have to have redundancy to keep the system operating autonomously for such a long time. The control system architecture has changed, and we have increased fault detection and handling. We have active control, and we have thrusters and a dual counter-rotating propeller to make the system more stable. And this is how it looks like. So the pressure housing for the storage, control electronics and the payloads, and then the configurable bays for battery and additional payloads. And it has active ballasting, so this is important if you are working in different environmental conditions in terms of temperature and salinity in the ocean. And you have to have different ballasting to counteract the environmental conditions which we put in place. And we needed more reliability and self-awareness and redundancy in the electronics. And this is what we came up with in the end. So the vehicle is 11.8 meters long. It has a diameter of 1.2 meter, 8 tons weight, a depth rating of 6,000 meters, endurance of 380 hours or 15 days, and a speed range of 2 to 5 knots, a range capability of 2,400 kilometers, a navigation accuracy of 0.04% of the distance travels as the error of navigation. And we have a configurable payload bay of 1 cubic meter, and we can take 1.5 tons of payload. And it's designed to deliver payload as well. Not operate only on the vehicle, but we are able to deliver a payload. And that is specifically important or interesting for naval applications as well. So we set out to do this. We had a contract when we first set out to do it. So a customer gave us a contract for a system and asked us to develop it within 18 months. And we did it. So that was placed last year. So just September this year, 2 months ago, not even 2 months ago, we had the first mission of the vehicle. So the system stayed out for 16.5 days in a fully autonomous operation. So there was no communication or positioning update with the vehicle while it was operating. The water depth was in the North Sea, close to Norway, operating in water depths 50 to 3,400 meters. That's as deep as the North Sea goes. And we covered above 2,200 kilometers, and the positioning error from when it dove down to when it came back up was 440 meters in actual position to where this system thought it would be, which equates to 0.2% of the distance traveled. And the data set required is full data sets, synthetic active sonar, multi-beam camera, and laser data. And it's a world record for autonomous operation on this scale. And this is concluding my presentation, and I would like to thank you for your attention, and I hope I could give you some information about my company and give you an example of what we are doing with a very recent example of the development of the autonomous system. So thank you very much.
네, 오늘 마틴 발표를 진행해 주셨습니다. 다시 한번 뜨거운 박수 부탁드리겠습니다. 네,